Hi, can you solve this simple Harvard University entrance examination question? Well, it's very simple but tricky. In case you have tried, you notice that there's no how you can use ordinary algebraic method to directly get the answer of the value of x because of it's a kind of a transcendental equation. So now how can we now solve transcendental equation like this? Now, it's very simple. To solve this transcendental equation, because we can't use normal algebraic methods, we're going to be using a function known as a Lambert omega function or a product log function. In case you are hearing of it for the first time, it's not hard, it's very simple. What does Lambert omega function mean? How is it used? It's very simple. Whenever you have an exponential equation in this format, a variable Euler's constant e raised to the power of that same variable equals to a constant or a number. Whenever you have an equation of this format, right, you can easily use Lambert's function to get the value of the unknown variable. But the variable can be a letter, okay, in our case x, and the constant can be a number. To understand Lambert's function better, let's make a comparison between Lambert's function and trigonometric function. So let's give one equation. Let's actually have an equation like x e raised to the power x equals to 0.5. Same way we have sine x equals 0.5. So from trigonometric function, if you want to get the value of x, of course we take arc sine of both sides. So that will be arc sine x, then arc sine 0.5. We know arc sine will cancel sine, will remain x. Then arc sine of 0.5 using our calculator will give us 30. That same way, if you want to calculate an equation in this format, right, we can't use trigonometric function. We're going to use Lambert's function or product log function. So you take Lambert's function on both sides, just like I've done here. Lambert's function on this side, then Lambert's function of this here. The Lambert's function of an exponential equation in this format, we cancel it out. So this Lambert's function is like the inverse of an exponential equation looking like this. So Lambert's function will cancel this format, then it will remain just s. Then equals to Lambert's function of 0.5. It will give us approximately 0.3517. Now you might be wondering that why is this useful to us, because our equation doesn't look anything like this. So then how can Lambert's function be helpful? Well, when you have an equation like this, you have only one target. That target is to try as much mathematical manipulation you know, just to make sure your equation looks exactly like this. Now, at every point in time of our solution, we're comparing this our equation with our guide here. I'll call this guide, okay, our guide equation. Now, first of all, let's compare these two. We'll see that in this we have just one term of the variable and the constant in front, but here we have two terms of the variable and one constant. So we have to try to do something about that. What we're going to do is that we're going to transpose x to the other side. So that will be 2 raised to the power x equals 20 minus x. Okay, let's make it a term by putting a bracket, right? Now, that's the first comparison. For the second comparison, now we'll see that our equation now have two terms of x, but we ought to have one term of x and one constant. Now, to have this, let's divide both sides by 2 raised to the power x. So I'll divide by 2 raised to the power x, divided by 2 raised to the power x. 2 raised to the power x cancel 2 raised to the power x. And we have 1 equals, we are making progress bit by bit. Let's flip this equation. So 20 minus, and now you can see that we're making big progress because we have a term of x, we have one term of x, we have a constant, we have a constant. We are making progress bit by bit. Now the next thing is that when we compare here, we'll see that there is no fraction here. We have a fraction here. So let's try to eliminate this fraction. And to eliminate this fraction, we're going to use law of indices that states that 1 over a raised to the power b will give us a raised to the power negative b. So I'm going to do that here. Times 2 raised to the power negative x will be equals to what? 1. Slowly, we're getting there. Now, let's compare it once more. When we compare it, we'll see that in our guide equation here, the variable as there is a coefficient here must be the same as the power. Okay, must be the exact same thing, no difference. Now, our coefficient here, 20 minus x, is different from this negative x here. Let's try and make this power have positive 20, just like this. So multiply both sides by 2 raised to the power 20. So that will be 2 raised to the power 20 equals to 1 times 2 raised to the power 20. Multiply both sides by this. Then from law of indices, we add this power together. So now it plus 20 equals to 1 times 2 raised to the power 20 is 2 raised to the power 20. So let's rewrite this. We have t minus x equals 2 raised to the power 20. Now, instead of making a big progress, I've made this coefficient and this power exactly the same thing. A constant, nice. But we are left with just one more problem. In our guide equation here, the base is the Euler constant E, but here we are having 2. And for Lambert's function to be useful for us, the base here must be E, not any other number, must be that E. So now how can we make these 2 vanish and become E? It looks hard. It's very simple. I'm going to use law of logarithm. What's law? From a law of logarithm, we know that when we have a raised to the power log b base a, when you have an index and a base that are the same thing, then the answer is going to be this b. It will be as if this will cancel out this log a and it will be b. That's the basic law of logarithm. Now, we can also invert it this way. It means that when you have a number or a letter b, we can express it in an exponential form like this, using a log of any base you like. So we can say 10 raised to the power log 10 base b will still give us what? B. Now it's this basic rule we are going to use. Now if we extend this rule, so we can now say 2 equals to a raised to the power log 2 base e. And now in mathematics, whenever we have log of a number and e is the base, you don't write it like this. We write it like lane 2. Let's continue. 2 minus x times, instead of writing 2 now, we'll now write a raised to power lane 2. So a raised to power lane 2, then raised to power 20 minus x equals to 2 raised to power 20. Because of e raised to power lane 2 is to give us 2. Let's expand this bracket. So we have 20 minus x times e raised to power lane 2 into bracket 20 minus x equals to 2 raised to power 20. Yes, we are making very big progress. We now have this e just like this. But now, because of this algebra we did here, there's not a consequence, which is lane 2. Now, our power is not different from our coefficient. We have lane 2 here. We don't have lane 2 here. And don't forget, these two must exactly be the same. So what we're going to do now about this, very simple, just multiply both sides by lane 2. Because lane 2 is a constant, so give us a value. So we can multiply both sides by lane 2. That will give us lane 2 times 2 raised to the power what? 20. Finally, our equation is now exactly of this format. Now let's make our comparison. The m as a coefficient here is still the same as the power here. Can you see our coefficient and our power is exactly the same thing? And we have a constant by the right hand side here. Lane 2 times 2 raised to the power 20 is a constant. Okay. Now, as we have gotten this, we can now use Lambert omega function to get the value of lane 2 20 minus x. Can you see? It's very easy. Now let's take Lambert function of both sides. So that will be Lambert function of lane 2 times 2 raised to the power 20. Okay? Like I said earlier, the property of Lambert function will now be left with this, which will be lane 2 times 2 minus 20. That will be equals to. Now, Lambert function of lane 2 times 2 raised to the power 20 will give us a specific value. We use our calculator, but let's just keep writing it here. Okay, then from here, normally, we'll now solve for x normally from here. Just like normal equation, solve for x. Don't be confused. This will give us a digit when we use our calculator, but let's keep on writing it like this. I don't want approximation. Now, we'll divide both sides by lane 2. Divide by lane 2. Divide by lane 2. Lane 2 cancel lane 2. We have 20 minus x equals to Lambert function of all over lane 2. We're making progress. So we'll transpose 20 to the other side. So we'll be left with negative x equals Lambert function of minus 20. Are you following? Minus 20. Are you following? Now, because of this negative, we multiply both sides by negative 1. So we have x will be equals to negative Lambert function of n plus 20. Are you following? Now we now have x equals to. Now we now input this directly into our calculator. I'll show us how. So Lambert function of lane 2 times 2 raised to the power 20 divided by 2 will give us what? 16. Negative 16 plus what? 20. Then x equals to negative 16 plus 20 is what? 4. Our final answer. X equals what? 4. 2 raised to the power 4 is what? 16. 16 plus 4 is what? 20. Yes, as simple as ABCs. Any equation that you can express easily in this format, Lambert's function can be of help. We have other hundreds and plenty of equations that Lambert's function can be helpful. So in my next video, I'll be solving more equations using Lambert's function to get the value of a variable. Even though you enjoyed this video, please like the video and share it so that other students can benefit from it. And also follow my page and follow me on YouTube for more exciting mathematical content like this. Till next time, bye bye.